Hello everyone, thank you for being here. So I'm a PhD student and this is my topic. So how to merge computer vision and robotics improve visual inspection planning. The reason why we are interested in this topic is related to sustainable manufacturing. So industry, as you know, they want to have products with really high quality. They want to produce components with really complex geometry, and of course, they would like to increase the outcome. At the same time, they would like to reduce the cost, reduce the waste, and reduce the production time. We are mostly thinking about die casting applications. So there are two main reasons. One is that there are huge incomes from automotive in this sector. And the other main reason is that there are really high dimensional accuracy, smoothness, and high productivity requirements. Here you can observe some defects that usually occurs on this type of objects. We have, for example, some cracks, blister, and so on. And these defects can be categorized in different ways. In my PhD, I'm mostly interested in geometry, so in those defects that we can observe from outside. Right now, the standard in visual inspection planning is based on the human, so usually it's not a inline inspection. Every component is removed from the production line and is manually inspected. This, of course, is time intensive, and there is also another problem that is related to the performance, as the performance of the inspection strictly depends on the employee expertise. For this reason, we are thinking about developing a different solution that takes into account robotics. So we would like to develop an automated visually quality inspection system. There are some requirements to do so. We need a robotic solution, an inline inspection, and high speed and high accuracy. A robotic solution is needed to improve the flexibility and reduce the human errors. The inline inspection is needed to keep the production time low. And when I'm talking about high speed and high accuracy, I'm meaning 30 seconds per part with an average accuracy of 0.3 millimeters. So our idea is to develop a system like this. We have some external specification from our customers, for example, where to inspect and how to inspect. Then there is the inspection, pose, and motion planning. That is the part in which I'm mostly focusing during my PhD. So how should we inspect the part in order to be really fast and cover all the surface? This is done on offline. Then there is an inline part, that is the part in which we actually gather the data. And finally, there is the quality control step, in which we do something with this data, like we reconstruct the model or we derive other metrics. The visual inspection planning can be formalized as coverage path planning. So as I said, there are some external specifications. For example, the 3D model of the object that we want to inspect and the model of the sensor that we want to use. Then we generate some inspection poses, and then we derive a collision-free path in order to be able to inspect the part from all these parts. In this way, we are able to obtain an inspection plan. There are two main approaches in the state of the art. One that is computer vision based, and in this case, optimal inspection poses are generated based on the object, so based on the geometry of the object. And another approach that is robotics based. And in this case, the inspection poses are generated sampling the workspace of the kinematic setup. However, both methodologies have some limitations. In case of the computer vision method, the inspection poses are optimal for the object, but given a specific kinematic setup, may be unfeasible. This means that the robot will not be able to place the end effector in correspondence of that pose. And in the case of the robotics method, of course, the inspection pose are feasible, as we computed them sampling the workspace of the kinematic setup, but some portion of the object may be uncovered. For this reason, we wanted to develop a new method that takes into account both computer vision and robotics. So first of all, we generate seed inspection poses based on the geometry of the object, and then we refine them, taking into account the kinematic setup. To do so, first of all, we need a method to generate these seed inspection poses. Then we need a metric to evaluate the coverage, so to know how well we can see with these inspection poses. And finally, we need a method to refine those unfeasible inspection poses. Here you can see the flowchart of the pipeline I developed. First of all, we generate these seed inspection poses based on the model of the object and of the sensor. Then we evaluate this feasibility and visibility evaluation, and we correct those viewpoints that are unfeasible. And finally, we solve the set coverage problem, that is an integer linear programming problem that provides us the smallest number of inspection poses to obtain all the data that we need. So there are in literature many methodologies actually to compute these viewpoints. What we did was to develop a new method that we call surface method. And the reason is that our method depends on the shape of the object, while some of the methods in the state of the art, they don't. There is a lower computational cost. It has just 2 parameters to tune, and is actually pretty intuitive to implement. What we do is that we have the 3D mesh. We apply Poisson desampling, so we have some sample on the object, and these samples are spaced from each other of a specific radius. And once we have them, we apply a standoff correction. This means that we move along the normal of this sample of a distance equal to the working distance of the sensor. In this way, we are sure to have our object in focus. And finally, if there are some occlusions between the line of sight of the sensor with the sample that generated it, then we correct them. And in this way, we have our inspection pose candidates. We compare our method with other methods of the state of the art on three different objects that actually were already evaluated in the state of the art. And we found out that surface sampling methods, and in particular Poisson disk sampling, is the one able to achieve full coverage with a number of optimal inspection poses or viewpoints that is lower or comparable to the other methods. So at this point, we have some inspection poses, and we need to evaluate them. So usually the evaluation is done via ray tracing. This means that some rays are traced from the focal point of the camera through the scene. And based on what each ray hits, we are able to understand what we will see from that specific inspection pose. And these information are stored in a matrix that is called visibility matrix. This matrix is defined as 1 if a surface element can be seen from a specific viewpoint, or 0 otherwise. So for example, in this slide, you can see that Vij is equal 1 because the viewpoint I is covering the surface Si, but Vi plus 1j is equal 0 because in that case, that surface element is not covered. This definition presents, however, some limitations because when we are in this situation, you can see that we have one inspection pose, and you can see that there is just one ray that partially hit a face. So with the standard definition, we would just that the face Si is visible. But actually, I would say that this is not well seen. There is a big portion of the face that is not covered. So what we did is that we started from the concept of spatial resolution that relates the area of the image sensor with the number of pixels, and we derive the surface element density. So in this case, we don't use the number of pixels, but the number of rays hitting a surface element, and we don't use the area of the image sensor, but we use the area of the surface element that we hit. So when we are in the situation like the one on the left, in which you see that there are two inspection poses, in which one inspection pose is covering for real the object with the surface element density that we want, then we use not 1 or 0, but a normalized value. So the normalized surface element sampling density. When this is not the case, like on the right, then in that case we use the standard visibility matrix because we prefer to cover one face with at least one ray than not see it at all. Once we have this matrix, then we solve the set coverage problem. And here you can see that when we use the standard visibility matrix, we have many areas that are in blue there, while when we use our sampling density matrix, we have many areas in red, where red means higher density, so more points in our point cloud. And this is actually what we want. And also, if you look on the plot on the right, when we use the sampling density, we are on the left of the target spatial resolution. That means we are able to obtain a spatial resolution smaller than what we wanted, and this is good. When we use the visibility matrix, then we have some surface elements that are covered with a worse resolution. So at this point, we have some inspection pose candidates. We have a way to evaluate them, but actually it can be the case that some inspection poses that we design are not feasible, because the feasibility depends on the kinematic setup that we want to use. And for example, if you have a setup like this one in the picture, you have just 3 degrees of freedom. You have a linear axis, a turntable, and a goniometer. Maybe you want to use such a setup because it's cheaper, or maybe because you can have higher precision with respect to a robot. So we need a way to correct, to improve those unfeasible inspection poses. And what we did is that we developed an optimization pipeline based on Bayesian optimization, in which we start with an unfeasible inspection pose. First, we apply an orthogonal projection so that we are sure to have some initial valid solution. And at that point, we start an optimization routine in which, first of all, we try to find a new feasible inspection pose that provide the same coverage, so that is covering those faces that were covered from the unfeasible inspection pose. Then we would like actually to find a feasible pose that can see what was previously covered, but even something more, if it's possible. And finally, there is a third term that aims to cover those phases that are actually not covered already from other feasible viewpoints. In order to validate our method, we compare it with other 2 methods. In case of workspace sampling, what we did was to sample the workspace of the robot. So in that case, we are sure to have feasible inspection poses that actually are not optimal for the object. And in case of the box constraint, we apply just an orthogonal projection from the unfeasible space to the feasible space without adding any optimization procedure. And we evaluate these 3 methods on different objects, like rabbit that is more convex and concave, this bracket that has some holes, a parallelepiped that is sharp, and finally a gear and a hair that have some self-occlusions. Here you can see some results. So actually our method that is indicated as BO is the one that is able to achieve highest coverage with a number of optimal inspection poses that is lower or comparable to the other methods. We also validate our method with real experiment. So here we have the setup that I was showing before. We have a single stage axe, a turntable, a goniometer, and a 3D printed plastic rabbit. And we use structure light sensor. In this case, it was Zivit. We also had a digital twin in which we were able to evaluate how the object was going to move. And the object moves on the setup so that the camera can acquire point clouds from different views. And then these views are stitched together, for example, with global ICP or generalized ICP in order, for example, to reconstruct a 3D model. Here you can see some point clouds that we obtained from the different objects. And what we did was also to compare the 3D printed plastic bracket with a die-casted one. The idea was to evaluate how different surfaces impact on the same geometry, and we were able to inspect both objects and cover them fully. So this was our pipeline. Some remarks. We needed a method to generate seed inspection poses, and we did it with this Poisson desampling method. Then we needed a metric to evaluate how good these seeds are, and we defined a new metrics based on the spatial resolution. And finally, we needed a method to improve those viewpoints that were unfeasible. So in the future, we would like to implement this solution for redundant robots. We actually have, we are already actually able to implement it with a normal robot, like 6 degrees of freedom. It already works, but we would like to have, for example, 8 degrees of freedom or more. Of course, we want to keep experimenting on objects with different geometries and different material surfaces. And finally, we would like to improve speed, coverage, and accuracy. Thank you. If you have questions, I'm happy to reply.
Thank you very much.